cogeneration plant that was installed at a hospital, involving combining 3 separate services into one 4000 amps 277/480 volt service along with a 600 kilowatts 277/480 volts 4-wire generator that parallels with a local utility, ran into an issue. The plant included a heat exchanger to heat a boiler for the central plant steam and provided 600 kilowatts of the campus power needs. After initial commissioning and testing, the unit operated smoothly for a few months. However, following a utility-mandated power factor adjustment, the generator began to trip constantly due to high neutral current. The neutral current relay was set at 50 amps, a value the generator manufacturer wouldn't budge on. Investigation revealed that the hospital's HVAC system used numerous 277 volts heaters, which caused fluctuating and unbalanced neutral current as they switched on and off. A proposed solution from the maintenance contractor, a neutral current resistor, was deemed inappropriate as these are designed for ground fault situations, not unbalanced neutral current. The generator manufacturer's unwillingness to allow more than 50 amps of return current, despite the alternator being rated at 1 megawatt, added to the complexity. Since changing the load was not feasible, the only viable option seemed to be increasing the relay setting or installing a 480 to 277/480 volts isolation transformer, the latter being a costly option. A less expensive alternative was to find the worst current imbalance within a 277/480 volts panel and install a smaller transformer there. However, this option would require approval, which can be a lengthy process. Possible solutions include firstly, increasing the neutral current relay setting. Adjusting the neutral current relay to a reasonable value that does not trip the generator unnecessarily may be a solution. This may require the generator manufacturer's approval. Secondly, installing an isolation transformer. A 480 to 277/480 volts isolation transformer between the cogeneration plant and the hospital service would isolate the neutral current from the hospital's unbalanced loads. This is an expensive option, but it would solve the problem effectively. Thirdly, distributed correction. Install smaller transformers throughout the hospital to balance the neutral current locally. This approach may be more cost-effective than a single isolation transformer. However, it may still require approval. Fourthly, using a neutral reactor. A neutral reactor can be used to increase the impedance of the neutral current path, reducing the current through the relay. This solution may be less effective than an isolation transformer, but it is less expensive. Fifthly, rewiring the HVAC system. A long-term, but potentially expensive solution may be to rewire the HVAC system to eliminate the unbalanced loads that are causing the problem. This may involve replacing the 277 volts heaters with more balanced 480 volts units. The validity of the generator manufacturer's claim that the neutral current relay must be set at 50 amps is questionable. It is possible that the generator has a sensitive neutral grounding scheme that requires a low relay setting to protect against ground faults. However, it is also possible that the manufacturer is being overly conservative and the generator could safely operate with a higher neutral current setting. To move forward, engage with the generator manufacturer to explore reasons for the low neutral current relay setting. Thoroughly investigate the loads in the hospital and identify the sources of unbalanced neutral current. Consider the most cost-effective solution, which may involve a combination of approaches, such as increasing the relay setting and installing a neutral reactor or distributed correction transformers. In more detail, let's consider the neutral current relay setting. The initial step involves scrutinizing the existing 50 amp setting. This low threshold, as specified by the generator manufacturer, appears to be the root cause of the frequent trips. The fundamental question is whether this setting is genuinely necessary for the generator's safe operation or if it's an overly conservative measure. Begin by thoroughly reviewing the generator's technical documentation. This documentation should provide detailed specifications regarding the generator's neutral grounding system, its capacity to handle unbalanced loads, and the recommended settings for the neutral current relay. Pay close attention to any clauses that justify the 50 amps limit. Engage in a direct dialogue with the generator manufacturer's engineering team. Request a comprehensive explanation for the stringent 50 amps limit. Challenge them to provide empirical evidence or simulations that demonstrate the necessity of this low setting for preventing damage to the generator. Inquire about the potential consequences of slightly increasing the relay setting, such as to 60 amps or 75 amps, and whether such an increase would compromise the generator's protection or stability. Seek clarification on the generator's neutral grounding system. Is it a solid grounded system, a low impedance grounded system, or a high impedance grounded system? The type of grounding system significantly influences the magnitude of fault currents and the sensitivity required for the neutral current relay. If the generator utilizes a high impedance grounded system, a higher relay setting might be permissible without compromising ground fault protection. Investigate the possibility of temporarily raising the relay setting to a slightly higher value, such as 60 amps, for testing purposes. Carefully monitor the generator's performance under this increased setting, paying close attention to parameters like neutral current, voltage balance, and temperature. If the generator operates without any signs of distress or instability, this could provide evidence to support a permanent increase in the relay setting. Before making any changes to the relay setting, consult with a qualified electrical engineer who possesses expertise in generator protection and coordination. This engineer can independently assess the situation, review the generator's technical documentation, and perform simulations to determine the optimal relay setting that balances protection and operational reliability. If the generator manufacturer remains inflexible on the 50 amps limit, explore alternative relay technologies. Some advanced neutral current relays offer sophisticated features like harmonic filtering and adaptive settings. These features can potentially mitigate nuisance tripping caused by harmonic currents or transient imbalances, allowing for a slightly higher overall relay setting without compromising protection. Document every communication with the generator manufacturer, including dates, times, names of individuals involved, and the content of the discussions. This documentation serves as valuable evidence in case of future disputes or warranty claims. Emphasize the operational disruptions and financial losses resulting from the frequent generator trips caused by the overly sensitive relay setting. This can provide additional leverage in persuading the manufacturer to reconsider their position. Now consider installing an isolation transformer. A 480 volts to 277/480 volts isolation transformer is a robust solution for mitigating high neutral current issues in cogeneration systems, especially when dealing with unbalanced loads. The fundamental principle behind the isolation transformer is to create separate neutral grounding references for the cogeneration system and the hospital's electrical distribution system. This electrical isolation prevents the hospital's unbalanced loads from directly influencing the generator's neutral current, thereby reducing the likelihood of nuisance tripping. The primary advantage of an isolation transformer lies in its ability to completely decouple the neutral current flow between the generator and the hospital's electrical system. By creating a separate neutral reference, the transformer effectively blocks any circulating neutral currents caused by unbalanced loads, harmonic currents, or ground faults within the hospital's distribution system. This isolation ensures that the generator's neutral current remains stable and within acceptable limits regardless of the load conditions on the hospital side. When selecting an isolation transformer, it is essential to carefully consider several key parameters, including the transformer's kilovolt-ampere rating, voltage ratio, impedance, and insulation class. The kilovolt-ampere rating should be sufficient to handle the full load of the cogeneration system, typically around 600 kilowatts in this case. The voltage ratio should match the system voltages i.e. 480 volts to 277/480 volts. The transformer's impedance should be chosen to provide adequate fault current limitation while minimizing voltage drop under load. The insulation class should be appropriate for the operating environment, considering factors like temperature, humidity, and altitude. To ensure proper operation and protection, the isolation transformer should be equipped with appropriate protection devices, such as overcurrent relays, differential relays, and ground fault relays. These relays provide backup protection in case of transformer faults or abnormal operating conditions. The relays should be coordinated with the generator's protection system to ensure a selective and coordinated response to faults. Installation of an isolation transformer typically involves several steps, including disconnecting the existing generator feed, installing the transformer in a suitable location, connecting the transformer to the generator and the hospital's electrical system, and commissioning the transformer. It is crucial to follow all applicable electrical codes and safety regulations during the installation process. A qualified electrician should perform the installation to ensure proper wiring, grounding, and bonding. After installation, the isolation transformer should be thoroughly tested and commissioned to verify its proper operation and performance. This includes performing insulation resistance tests, turns ratio tests, polarity tests, and voltage regulation tests. Transformer's protection relays should also be tested and calibrated to ensure proper coordination with the generator's protection system. While isolation transformers are effective in mitigating neutral current issues, they can be a relatively expensive solution compared to other options. The cost of the transformer itself can be significant, and additional costs may be incurred for installation, protection devices, and commissioning. Therefore, a cost-benefit analysis should be performed to determine if the benefits of the isolation transformer outweigh the costs. Now consider distributed correction. Distributed correction is an alternative approach to mitigating high neutral current issues in cogeneration systems that involves installing smaller transformers throughout the hospital to balance the neutral current locally. This method can be more cost-effective than a single large isolation transformer, especially in facilities with multiple distribution panels and dispersed unbalanced loads. The fundamental concept behind distributed correction is to address the sources of unbalanced neutral current at their point of origin. By installing small, strategically placed transformers near the unbalanced loads, the neutral current can be reduced or eliminated locally, preventing it from propagating back to the generator and causing nuisance tripping. This approach is particularly effective in hospitals, where unbalanced loads are often distributed throughout the facility in areas such as HVAC systems, lighting circuits, and medical equipment. The first step in implementing distributed correction is to conduct a comprehensive load analysis to identify the sources of unbalanced neutral current within the hospital. This analysis should involve measuring the current in each branch circuit and distribution panel to pinpoint the circuits with the highest neutral current. Data logging equipment can be used to monitor the current over time and identify patterns or trends in the unbalanced loading. Based on the load analysis, small, single-phase transformers can be installed near the identified unbalanced loads. These transformers can be configured as either buck-boost transformers or isolation transformers, depending on the specific requirements of the load. Buck-boost transformers are used to adjust the voltage of the load, while isolation transformers provide electrical isolation between the load and the distribution system. The size and rating of the transformers should be carefully selected based on the magnitude of the unbalanced load and the voltage requirements. It is crucial to ensure that the transformers are properly sized to handle the load without overheating or experiencing excessive voltage drop. Distributed correction transformers can be installed in various locations throughout the hospital, such as near HVAC units, lighting panels, or medical equipment rooms. The transformers should be mounted in a safe and accessible location, following all applicable electrical codes and safety regulations. It is essential to ensure that the transformers are properly grounded and bonded to prevent electrical hazards. After installing the distributed correction transformers, the neutral current in the affected circuit should be measured to verify the effectiveness of the correction. If the neutral current is not reduced to an acceptable level, the transformer connections can be adjusted or additional transformers can be installed. The goal is to minimize the neutral current in each circuit to prevent it from contributing to the overall unbalanced neutral current in the system. Distributed correction can be more cost-effective than a single large isolation transformer, especially in hospitals with multiple distribution panels and dispersed unbalanced loads. The cost of the smaller transformers is typically lower than the cost of a large transformer, and the installation costs can be reduced by distributing the work among multiple locations. However, distributed correction can also be more labor-intensive than a single transformer installation, as it requires more detailed load analysis and coordination. Now consider a neutral reactor. A neutral reactor, also known as a neutral grounding reactor, is a device that can be used to mitigate high neutral current issues in cogeneration systems by increasing the impedance of the neutral current path. This increased impedance reduces the magnitude of the neutral current flowing through the generator's neutral grounding system, thereby preventing nuisance tripping of the neutral current relay. The fundamental principle behind a neutral reactor is to limit the fault current during a ground fault condition while also reducing the steady-state neutral current caused by imbalanced loads. The reactor achieves this by introducing an inductive reactance into the neutral grounding circuit, which opposes the flow of current. The amount of reactance is carefully selected to provide adequate fault current limitation while minimizing the impact on the system's voltage and stability. The effectiveness of a neutral reactor depends on several factors, including the system voltage, the size of the unbalanced loads, and the desired level of neutral current reduction. The reactor's impedance should be chosen to provide the optimal balance between fault current limitation and steady-state neutral current reduction. A reactor with too high of an impedance may excessively limit the fault current, while a reactor with too low of an impedance may not provide sufficient neutral current reduction. Neutral reactors are typically installed in the neutral grounding circuit of the generator, between the generator's neutral point and the grounding electrode. The reactor is connected in series with the neutral grounding conductor, so all neutral current must flow through the reactor. This arrangement ensures that the reactor effectively limits the magnitude of the neutral current during both ground fault conditions and steady-state imbalanced loading. When selecting a neutral reactor, it is essential to consider several key parameters, including the reactor's voltage rating, current rating, impedance, and continuous current capability. The voltage rating should match the system voltage, and the current rating should be sufficient to handle the maximum expected neutral current. The impedance should be chosen based on the desired level of neutral current reduction and the system's fault current requirements. The continuous current capability should be adequate to handle the steady-state neutral current caused by unbalanced loads. Installation of a neutral reactor typically involves several steps, including disconnecting the existing neutral grounding conductor, installing the reactor in a suitable location, connecting the reactor to the generator's neutral point in the grounding electrode, and commissioning the reactor. It is crucial to follow all applicable electrical codes and safety regulations during the installation process. After installation, the neutral reactor should be thoroughly tested and commissioned to verify its proper operation and performance. This includes performing insulation resistance tests, impedance tests, and voltage drop tests. The neutral current should also be monitored under various loading conditions to ensure that the reactor is effectively reducing the neutral current. Now consider rewiring the HVAC system. Rewiring the HVAC system to eliminate unbalanced loads is a long-term solution that can effectively address high neutral current issues in cogeneration systems. This approach involves replacing the existing 277 volts heaters with more balanced 480 volts units, which reduces the neutral current flowing through the system. The fundamental principle behind this solution is to distribute the electrical load more evenly across the three phases of the electrical system. When loads are unbalanced, such as when single-phase 277 volts heaters are connected to only one or two phases, the neutral conductor carries a significant amount of current. This neutral current can cause nuisance tripping of the neutral current relay in the cogeneration system, as well as other problems such as voltage imbalances and increased energy losses. By replacing the 277 volts heaters with 480 volts heaters, the load is distributed more evenly across all three phases. This reduces the neutral current and improves the overall balance of the electrical system. In addition to replacing the heaters, other HVAC components such as motors and fans can also be rewired to operate at 480 volts. This further reduces the neutral current and improves the system's balance. When rewiring the HVAC system, it is essential to follow all applicable electrical codes and safety regulations. A qualified electrician should perform the work to ensure that the wiring is done correctly and safely. The new 480 volts heaters and other components should be properly grounded and bonded to prevent electrical hazards. It is also crucial to consider the impact of the rewiring on the existing electrical system. The existing wiring and circuit breakers may need to be upgraded to handle the increased current and voltage. The system's protection devices should also be re-evaluated to ensure that they provide adequate protection for the new loads. While rewiring the HVAC system can be an effective solution for reducing neutral current, it can also be an expensive and time-consuming project. The cost of the new heaters and other components can be significant, and the labor costs for the rewiring can also be substantial. Additionally, the project may require extensive planning and coordination to minimize disruption to the hospital's operations. In conclusion, several options exist for addressing the high neutral current issue: increasing the neutral current relay setting, installing an isolation transformer, implementing distributed correction, utilizing a neutral reactor, and rewiring the HVAC system are all potential solutions. Each option has its own set of advantages and disadvantages, and the best choice will depend on the specific circumstances of the installation. It is crucial to carefully evaluate each option and consider the cost-effectiveness and potential impact on the hospital's operations before making a decision.